Hello, everyone, and welcome to episode 47 of the Hyperthesis. I'm Patrick.
I'm Feely.
And I'm Liam.
Well, we have a super spaced out episode for you today, as we'll be talking about a lot of different space-related things, including a very star-studded main topic from Liam. But before we start there, let's talk about some science in the news recently.
Yes, I had our intro topic all prepared today on tsunamis, but then this news came out and I was like, oh geez, I better talk about this or people will get upset. Which it's good news. But anyway, on Wednesday, the North American Nanohertz Observatory for Gravitational Waves, or NANOgrav as people have been calling it, or I guess that's what they call themselves. It's this international collaboration, and they revealed evidence for the existence of a low-pitch hum of gravitational waves that reverberates across the universe, everywhere. So I guess on Wednesday they announced that, and on Thursday they streamed like a public news briefing to officially make this announcement to the public. So I would go look into that if you're interested. I don't know how much we've talked about gravitational waves or how much I should introduce them, but gravitational waves are these waves produced when things accelerate in space-time. So for example, if you have like two black holes orbiting one another, or even, if me and Feely held hands and spun in a circle, like a nice romantic couple. Although those gravitational waves would be very tiny. But they're like, think of sound waves and water waves. They have to travel through a medium. Electromagnetic waves don't. They can travel through kind of the vacuum of space. But gravitational waves are even weirder. They actually propagate as these ripples in the very fabric of space-time, whatever that is. So you can think of it as like you have a really still pond and you kind of throw a rock into it and you get these ripples that propagate out from where the rock hit. Something similar happens with gravitational waves. If you have like two black holes spinning around each other, they produce these wiggles in space-time that move at the speed of light. So as gravitational waves pass through you or any other object, they warp the space-time that we exist in, and that can actually change how far apart things are. So if a very weak gravitational wave passes through you, it can cause the distance between the atoms in your body to shift a very tiny amount. And yeah, there's a lot to talk about for an intro topic, but there's very interesting stuff. And in 2015 and 2017, LIGO, which is something we've talked about a lot, the Laser Interferometer Gravitational Wave Observatory, they were the first kind of group to detect gravitational waves from these black hole mergers and even neutron star mergers. And the amount of precision you need, so the sources of gravitational waves, they're very kind of few and far between. And even the really powerful ones, they're so far away that by the time the gravitational waves reach us, they're just so minuscule that the sensitivity they have in their detectors, they're able to measure the change in distance of one thousandth of a proton. So very tiny distances.
One of the big challenges to do that is to stabilize things because like you're on a moving earth, right? So you have to be very careful and also to put things in perspective too, because think of it like, you put a drop of water onto a lake, right? And if you're close to the impact, you can see the wave propagating out. But imagine you're on the other end of the lake and you want to measure that, there is some wave, a drop of water in the middle of the lake happens. Like it's incredibly sensitive.
Now imagine that little drop hits the middle of like a Great Lake, when like Lake Ontario or something, and then you're at the edge. Like it's so tiny that you'll never see it.
Although to be fair to them, these are still massive events, and like you said, if you and Feely were holding hands spinning around each other, I would say that's more equivalent to a drop, where this is like a boat going through Lake Superior, let's say, and then you're trying to record it, because these are some of the largest gravitational waves that we're seeing from these massive events. But just
Well, but the thing is too, like the black holes that making these events are in like kilometer size, right? Like or even like meters, kilometer size. But the distance from us to there is like light years. So in a way, the size of the event is minuscule. It's like even smaller than dust, right? Like compared to like how much it has to travel.
It's like if I'm on the shore of the Atlantic and a submarine implodes in the ocean, in the middle of the Atlantic. I'm not going to notice it unless there's a lot of news coverage.
oh boy. Anyway,
It wasn't a submarine, but yeah.
Yeah, the quote unquote submarine.
going back to this breaking news. So that's how LIGO was able to detect these gravitational waves with very advanced technology. But how were they able to detect these specific perturbations?
Yes. So back to LIGO just quickly is that it's a huge deal that you can actually detect gravitational waves because I mean for a theorist it's like yay Einstein was right again, which it's usually true. He's right until you get to the kind of quantum gravitational regime. But also it's the first way that we can actually observe space without our eyes, if that makes sense. So all of our astrophysics and observations have been through optical telescopes or things like that. And it turns out if you can't see it, you can't really observe it. And now this is a new way to quote unquote see what's going on out in space. So we can detect things that we can't see with our eyes or with telescopes.
Well, I think to note on the Einstein predictions too. I think the things that he predicts so far on relativity and stuff has been proven correct. But the things that have not been proven correct, I don't think we said wrong, right? But I don't think there's any evidence on that part yet in quantum gravity because like there are many theories, but it could be possible in the future that it turns out that he was right. Who knows, right? But I think that part we just don't have experimental evidence yet.
Yeah, it's commonly accepted that Einstein's theory is wrong when you combine it with quantum mechanics. Well, one thing, it doesn't give you the right cosmological constant, which we know what that is from observation. But we've talked about that. I'm not going to get into that right
Yeah,
now.
so it's a debate. Should there be a cosmological constant and such, right? So
Yeah.
that was
Well, I
another
think
episode for another
most
day.
people think there should, but I won't get into it. Anyway, LIGO it won a Nobel Prize in 2017. Kip Thorne, Rainer Weiss, I might have said that last name wrong, and Barry Barish won this. So it was a huge deal. And the experiment itself was incredible. It was this massive thing. The sensitivity you need is insane. Like you said, if a car drove by 100 kilometers away, they could detect it. So it's crazy. So back to this NANOgrav experiment, which has been big in the news. What did they do differently? So, like I said, they found this evidence for this low pitch hum of gravitational waves that's everywhere in the universe. So LIGO could detect gravitational waves in kind of the frequency range of a few hundred hertz, which would have a wavelengths of about 3,000 kilometers. Oh, excuse me. And these were created by these kind of black hole neutron star mergers, like we said. But NANOGrav's looking for some much, much, much lower frequencies, gravitational waves in the nanohertz range. That's those have wavelengths of about 30 light years or 300 trillion kilometers. So they're very, very low frequency waves. And the reason why is because physicists suspect that these gravitational waves are actually the collective vibrations of space time of thousands to millions of pairs of supermassive black holes that slowly merge and whiz around each other and generate gravitational waves. But these black holes are much different than these smaller ones because they're very, very far away, like um, 10 billion light years roughly, and they'd be sitting at the hearts of galaxies in these very, very far away ancient galaxies. For reference, the age of our universe is about 14 billion years old, at least according to our current theory. Things always change, but and so basically, if you learn about these very long wavelength or low frequency gravitational waves, you could learn about how galaxies formed about 10 billion years ago or about 4 billion years after the Big Bang. Um, and there's also other things too. So there's other theories which some people believe that these gravitational wave background could also be coming from something else, like these hypothetical cracks in space-time due to cosmic strings. So maybe the string theory people are getting excited about this. I don't know enough about it to comment on it, but only time will tell. And then finally, one other thing is that it could tell us about the Big Bang itself. So one problem with the Big Bang is that, I mean, like I said before in previous episodes, we have one universe, one sample size, and we can't go backwards in time. So you can't go back and look at what happened in the Big Bang. So you have to look at kind of remnants of what happens. And one of them is called the cosmic microwave background. And that tells us up to about 400,000 years after the Big Bang what happened, but before that is very, very speculative. So presumably during the Big Bang, if gravitational waves came out of that, it would be almost instant. It wouldn't be like a 40,000 year delay until light could escape, like it did for the big inflation.
Just a quick side note with that. The reason why it took 400,000 years for light to actually propagate and what we see as the cosmic microwave background was that the universe was actually opaque. So when we look up into the sky now, we can see billions of light years away. But back then, it was dense enough and hot enough still that light couldn't really travel that far. And so when it transitioned from being opaque to being transparent or maybe even translucent, again, we're not quite sure even entirely what happened there. That's when the light could escape, and that's what we see as the cosmic microwave background, was all that trapped light. But yeah, light can't move through opaque things, so there you go.
Another thing that I would point out too is like, well, arguably absurd thing that human do, or even natural for us, right? We measure all these in years, but like a year is the time that the Earth revolve around the sun, and has nothing to do with the early universe. So I wonder if there's like another unit of time that people usually discuss. This is very natural for us to humans, right? Like, but does it even make much sense in cosmologically?
Yeah, I mean, there's this whole thing that we can get into about like absolute distance and absolute time, which is interesting to talk about. But I mean, we talk about years just because we're familiar with that, but we do have like light years as measurements of distance instead of like measuring the distance between the Earth and the nearest star in centimeters or meters. We have light years. So I'm curious if we
Well,
do have
light
any.
years also has something to do with the sun, right? Like it's still a year of light travel distance.
Absolute time confuses me. Um, Somehow, when you do general relativity and you look at this thing called an FRW metric, it's like this metric that you can use to model the inflationary universe or like the beginning of the universe. Somehow, there is an absolute frame of reference in it, and I don't know how physical that is. That it's I don't know the details. But when you say the universe is 14 billion years old, that's kind of meaningless, right? And I think somehow from this FRW metric you can calculate the I don't know. I have to look into this. I'll get back to you guys on that.
I will just say, isn't one of like the stipulations of relativity that there is no absolute time or absolute position?
Yeah, and that's what confuses me a lot. But I've seen it written down somewhere that there's this kind of absolute frame because it's like it's confusing because you're so used to thinking of space time as this infinite thing, but when you think of like inflation in the universe, it's like you can't do that, right? You can't think of it as this stuff that's
Well,
everywhere and
I think the point is to create a lab frame, basically. Like, what is a lab frame? Like,
yeah.
13.8 billions is compared to us as lab frame. I think that's how we can kind of make sense of it. If we try to manage like lab frame as the universe being created, then it's gonna be too confusing. Let's say we are here right now. This is our lab frame. What is the number of years back to the Big Bang?
Yeah. Anyway, we'll discuss this more in the future, especially
Yeah,
when Seam is able to look at that.
I
But
could be horribly misinterpreting what I read like a year ago in like a side comment of a paper. So I have to
but
double check that and get back to you. But so basically they the final how did they do this? How did they find that the way I'm imagining it, which maybe isn't the correct way, but imagine like you're in a pond and there's like it's windy and there's just waves kind of everywhere. That's the way I'm thinking of this. Is that like in space time there's all these waves going around everywhere at all times. They're just very, very low frequency and hard to detect. So to detect this background, the researchers did something which I think is extremely clever. So they didn't build a very expensive, large, crazy detector. They took advantage of the fact that there are these things called pulsars, which exist in our very own Milky Way galaxy, and these act kind of like a lighthouse. Um, they're these rapidly spinning stars, and they act like clocks. They emit beams of radio waves that can periodically be measured from the Earth. So Einstein's theory of general relativity tells us that as these gravitational waves propagate past pulsars, they should actually expand and shrink the distance between these objects and the Earth, changing the time it takes for the radio signals to arrive. And if there is a gravitational wave background, which is everywhere, pulsars across the universe should be affected by this in some kind of correlated or predictable way. So rather than build this crazy detector, um, they took advantage of already existing telescopes around the world. So there's some in New Mexico. I think it's called the Very Large Array. There's the Green Bank Telescope in West Virginia, and then there's this other one, the Arecibo
Arecibo.
Arecibo Observatory in Puerto Rico. Before its unfortunate collapse 3 years ago, which we might mention one day. So yeah, they basically just used radio telescopes, looked at these spinning pulsars, and kind of measured this time delay a little bit, or how they fluctuated somehow.
I will say this was also a great collaborative effort, but
Hmm.
in the sense of releasing everything at the same time, because there were 5 separate research groups spread throughout the world that were looking at this, and they were all able to coordinate and share these results at the same time. So their papers dropped. I think it was Wednesday, June the 28th, when they all dropped together. And so that took some coordination because imagine being the lab group being the first one to drop that and get ahead of it. But they collaborated all together and were able to get the results published and out. And having 5 separate labs confirm these results is incredible.
Yeah, one thing to be said though is I think they only have like a 3 to 4 standard deviation. It's just a measure of your error. And typically, when you do these physics experiments, if you have 5 standard deviations, it's okay. This is definitive proof. So they're not quite there, but there's a quote in the news article I was reading, and it was one of the physicists, and they were saying we've got 3 to 4. That's good enough for me, but we'll get 5 later.
Well, certainly very exciting. And we'll maybe have to do some more main topics on gravitational waves or pulsars, especially. Those are super cool. But do, with time in consideration, we will move on to our main topic, which Liam, I believe you are also talking about. Some very exciting and exotic things.
Yes. So I wanted to talk today about um, different types of stars. So in episode 40, which was actually focused on black holes, which maybe you can consider a black hole a star. Some people do, but I'm gonna keep them separate. Patrick, I think you ended the episode with a story on the life of a star. So you described kind of some more common types of stars like red giants and dwarfs and those kind of things. So if you're interested in kind of like the average star and the lifespan of them, go listen to that episode. But today we're going to be talking about, we're going to jump right over the basic stars and go straight to some fancier ones, so-called exotic stars. And there's also hypothetical stars, which I think they're different. I'd say an exotic star is made out of exotic matter, and a hypothetical one isn't necessarily. And I want to talk about both, but I think there's too many, so I'm just going to talk about exotic stars today. And in the future, I will talk about hypothetical stars because I have a friend named Riley who's very kind of interested in this kind of stuff. And he gave me a bunch of fancy hypothetical stars to talk about, which I want to, but I will do that another time. So anyway, what is an exotic star? An exotic star, it's something composed of exotic matter. So in other words, it's not made out of electrons, protons, or neutrons. It could be made out of things like quarks, for example, which is a type of star I'll talk about. So it's basically balanced. So when a star collapses, essentially what happens is it runs out of fuel, and the gravitational force pulls it in on itself. It's not balanced. It's not in equilibrium. So these exotic stars, they're balanced against gravitational collapse by degeneracy pressure or other quantum properties. So some more common types of stars, like neutron stars or white dwarfs, they're partially supported against collapse by these so-called neutron or electron degeneracy pressures, which is due to the fact that they're made out of fermions, so protons, neutrons, and electrons are all fermions. They're spin 1/2 particles, so they obey this thing called the Pauli exclusion principle, which I think a good amount of, if you've ever taken high school chemistry, you might have talked about this. But it's basically that fermions can't occupy the same quantum state, and because of this, you get this kind of quantum pressure that the Pauli exclusion principle. You can kind of treat it like this effective force that keeps them away. So neutron and white dwarf stars, this Pauli exclusion principle is what actually helps keep them stable. It's this degeneracy pressure.
Just to expand on the Pauli exclusion principle, again, if you were in chemistry in high school or in university, you may have heard of this, but there's so much pressure going on with these stars that the, say, electrons within the stars can't occupy the exact same space and have the same spin. So, for example, if you remember your orbitals from a hydrogen atom, you have your very basic orbital where it's just this kind of sphere of electron probability around a hydrogen, but you can have 2 electrons in there. So 2 electrons can be within the same orbital of the proton, hydrogen atom, but they have to be opposite spin. And so we use spin to kind of indicate the it's not a physical spin, and I think we've talked about it a little bit before.
Yeah, it's
But
just, you can think of it as just some quantum number that tells you kind of what energies or properties these particles have. Yeah,
but
not even the really really smart physicists out there know what spin is, so we're not
yeah,
alone.
but this spin is in a hydrogen atom, you can have 2 electrons in the same place, but one has to be spin up and spin down. And that's the only way it will work. If you have 2 spin up electrons, they can't be in the same orbital. So the same thing is going on here, but at much greater scale and with different particles.
Yeah, so these neutron stars and white dwarfs, they're very interesting. They're very cool stars, and this degeneracy pressure due to this Pauli exclusion principle is partially why they can exist. But for exotic stars, something similar can happen, but with these exotic matter, so actually like quarks and things. So exotic stars, yeah, they're mostly theoretical. Well, all the ones I'm going to talk about are theoretical, and those are the only ones I could read about. So I think they're all theoretical, and because they'd be pretty difficult to detect, um, and also partially because prior to gravitational wave astronomy, there was no actual satisfactory means of detecting them and kind of differentiating them from other objects as well. So maybe these new gravitational wave detectors could actually help verify or falsify these kind of theoretical exotic stars. But we'll see. So, out of all these proposed exotic stars, the kind of most well agreed, I guess the most likely one and the most understood is called a quark star. So, a quark star is a hypothetical star, and it results from the decomposition of neutrons into their constituent up and down quarks under gravitational pressure. So, just like how some massive stars collapse to form neutron stars at the end of their life cycle, um, it's possible, in theory, that for very extreme temperatures and pressures, the degeneracy pressure of these neutron stars could actually be overcome, and they could collapse even further, and the neutrons would be forced to merge and dissolve into their kind of constituent quarks. So protons and neutrons and electrons, they're all made of even smaller particles called quarks. And quarks have their own weird things going on with them. I think they have third they have spin that goes like 1/3, for example. So like one quark will have a spin of 1/3, whereas like fermions and bosons typically have spins of 1/2 or 1, and then integer multiples of them. I think. I'm not a particle physicist, so anyway, yeah. So after it's possible that these neutron stars could actually kind of collapse into quark stars, creating a really really dense phase of this packed quark matter. And in this new state, a new equilibrium could emerge, and this new kind of quark degeneracy pressure could stop the star from collapsing on itself. So these stars would be a lot smaller and denser than that of a neutron star, which are already pretty small and dense. And but we've never seen one. So they might be real, they might not be.
So, just a quick aside for quark stars was something I remember hearing about many years ago, and I was like, oh, that's cool. And it was specifically a strange star. I don't think you have this in your notes.
No, I was because when you look it up online or you kind of look into it, it's just the definition of a strange star is a quark star but made with strange quarks.
So,
So,
so the cool thing about the theories around strange stars are that they're kind of like
well,
the next. Oh,
what's a strange quark? I know that
okay,
there's 6 different types of quarks, right? There's like up, down.
String charm, top, bottom.
Yeah, so they're all quarks with slightly different properties, and somehow there's these 2 strange ones. Maybe these quark stars can be made of them.
yeah. So, okay, quick side note on quarks: there are 6 types of quarks, and then they of course have antiquarks. But they're the main one that almost everything that we interact with that are made up of are up and down quarks. Those make up the protons and the neutrons and the atoms. Now, quarks are elementary particles, so they can't really be broken down further from what we know so far. But we have the up and down quark, and then we have the strange and charm quark. So these were the next 2 to be discovered. They are identical in terms of charge to the up and down quarks, but they are heavier. And then we have the top and bottom quarks, which are the heaviest quarks, and they don't really last for very long. And I will say that the charm and strange quarks also don't really last for very long when they're isolated or when they're in particles like hadrons or other types of hadronic material.
So,
Oh, since
okay.
since we are talking about star formation, I want to point out actually today is the last day of the I think International Star Formation Conference in Lyon in France, and some of my colleagues are going there for I don't know what do you do in France, right? But I think there are still a lot of heavy duty research and people try to understand the star formation. There might be many theories, and what we talk about are like the accepted theories. I'm sure there are many more postulates and hypotheses or even data analysis that's being done right now to figure out how these strange stars, well, strange, but like unconventional star or like some a little weird stars are being formed. But then maybe there are more exotic stars that we don't know about because like we are not experts in star formation at all. Maybe we should get some of those people on the show.
Yes, I agree. And even in the more like commonly accepted and known stars like neutron stars, we still don't really fully understand what's going on inside of them. And even our own star near the Earth, like there's so much these people probably talk about that's just way beyond us at the moment.
Just going back to strange stars quickly, though, the really neat thing about them is their progression of these quark stars if they collapse enough but still remain not black holes. And within strange stars are what is known as strange matter, which I was like, oh yeah, it's matter that we don't know about. But it's actually matter that's only composed of strange quarks. And there are some suggestions or some theories that at very small scales or very small quantities, strange quarks are quite unstable. They will decay quite quickly into your up and down quarks, which are the most stable. We don't know if those actually decay. However, when you get more and more strange matter together, it's able to essentially affect each other and last for longer. And so these strange stars, which are quark stars, might be examples of significantly longer lived strange quarks, which form strange matter, which is a whole other topic. But it's this idea that the more strange quarks that you have all together, the longer that they will live, which is not really true for collections of quarks because as you have more and more together, typically they'll become more unstable and decay. But the opposite is hypothesized to be true for strange quarks. But we can't really produce that in the lab because we don't have the ability to make the center of a neutron star with only strange quarks. But it's just a really cool concept.
Yeah.
You can make that in simulation, I guess.
Well,
But I don't know
actually,
how effective that'd be.
you can
True.
do computer simulations, and also, and one of the topics in this analog gravity stuff I study is simulating neutron stars with ultra cold systems and things like that, which I don't know much about, but it's a nice idea. Anyway,
Wait, you simulate stars, which normally we think of star as like very hot, but you do it in an ultra cold system.
yeah, well, you just tune your system so that the mathematics is the same. Doesn't it's physically completely different, right? But anyway, I don't actually know about that. I've just there was a couple talks talking about it, how they were making analog neutron stars and things like that. But yeah, so those are quark stars, and also those strange stars, which are kind of like this subfield of quark stars. Um, I've got some other weird ones. One of them is called an electroweak star. So, um, who here knows about the electroweak force more than I do and can briefly introduce it? Excellent.
Yeah, so the electroweak force is essentially combines the electromagnetic forces and weak forces. And at some point in the early universe, it's most likely that these forces were actually the same thing. So you had gravity kind of driving off somewhere, and then the strong force, but then you had still the electroweak force combined. And when you do some QFT, I believe you can do some electroweak interactions, and it's complicated, but essentially it's the electromagnetic force and the weak nuclear force, which dictates atom decay and
Hmm.
all that stuff.
Yeah, you get
They're combined.
neutrinos and things. I think you need the weak force to describe how neutrinos come out of decays and things like this. Or maybe I'm wrong.
Yes. Yeah. And as with any force, it has its own bosons, which we'll be talking about a bit later. But
Has
yeah, so
those
they have their own.
WZ bosons.
Yeah. It's got 3 bosons.
Yeah. Um. Anyway, so an electroweak star, as you might guess, is related to the electroweak force, and it's this theoretical exotic star that could form after a supernova, where the gravitational collapse of a star is actually prevented by the radiation pressure um, that results from the electroweak burning, which is the energy release by the conversion of quarks into leptons. And leptons is just a fancy way of saying like electrons, muons, tauons, and neutrinos. So electrons, tauons, and muons are all kind of just different mass electrons. And neutrinos are these very, very, very light particles. They have very, very little mass, and they can go through things. So I think it's something like in your thumbnail, there's like a few billion neutrinos passing through it at any given second from our sun. But somehow in these electroweak stars, due to this really strong pressure, these quarks they'll decay into leptons, and the radiation pressure of this decay is enough to stop the star from collapsing. So physically, inside of a star, some star that's collapsing such that this occurred, there would be a volume of the star's core that would be approximately the size of a baseball that would contain. It'd be about 2 of Earth's masses, so it's a very heavy baseball. Um, and that's where this electroweak process would be happening. And so these electroweak stars, I'm not sure if you would just call the little baseball thing inside of the primary star the electroweak star, if you call the whole thing the electroweak star. Um, but they'd be denser than quark stars, and they could form when the gravitational attraction can no longer be withstood by the quark degeneracy pressure, but could still be withstood due to this electroweak burning radiation pressure. So they could actually be the next stage of life of a quark star potentially. So when a quark star somehow goes supernova, I guess. Although I'm not sure how that would even work or why that would happen. But yeah, this is a bit beyond me. So it's just interesting that there's kind of like all these different types of stars, and there's even one that involves the weak force. Because typically, when you think about the weak force in physics, it's like these it's weak, right? Like stuff like this doesn't seem to happen very much, where you have this very strong event due to it.
I know very little about any of these. You know, we have done a little bit of like nuclear physics here and there, and particle physics here and there, but like I didn't even know they could form a star. I just believed at the time, I think, for a long time that like there's very low probability that that would happen. Then it wouldn't happen at all, even in this vast universe. Or the probability that us finding it might be absurdly low that we never see it.
Yeah, I had no idea this about this stuff either, and I'm definitely not the world's leading expert. Um, I'm basically here to be a glorified version of Wikipedia and just tell you what I read somewhere.
Yeah, there's one of the things I thinking about, like, well, are these predictions help with the confirming the theories? Are these like exclusive things that's like, oh well, if we find this kind of electro weak star or like strange star, it would confirm specific theories, or it's just like something that we know that should really be true that we're just looking for it. So I don't know if which way it's going right now in the literature.
I think my guess is that people just came up with these ideas and said, "Hey, what if?" And then they did some math and they showed like, "Oh, this is a possibility." But for the example of the quark star, actually, there was some observations released by the Sandra X-ray Observatory in 2002. I might have pronounced that wrong, but basically, there's one star that they observed, which could be a quark star candidate, and it appeared it looked like a neutron star, but way too cold to be a neutron star, um, suggesting it was made of some denser material. So maybe that's a quark star. So I guess to answer your question, I think people come up with these ideas, and again, maybe I'm wrong, but they come up with these models. They say, "Hey, a quark star might exist, or an electroweak star might exist," and then later in time, maybe you get some data from observations that it says like, "Oh, this doesn't match what we know. It must be something new. Maybe it's a quark star." For the electroweak star, I have no idea how you would even predict that because it's like it's inside of another star, so I don't even know if you could detect it. Maybe you could detect it through a lot of neutrinos or something. But stars already emit a ton of neutrinos, let alone, um, and we struggle to measure those. We have these massive neutrino detectors, and even though there's billions and billions and billions of them passing through it every second, you can only detect like a few of them a year or something like that. It's crazy. So, yeah, I don't know. I think the quark star, like I said at the very beginning, I think it's the most kind of agreed upon that this could exist. There's some candidates out there, things that don't match what we know and could be quark stars. The other ones I think are a bit more theoretical, and the one I'm about to describe to you is very, very theoretical. I just thought I'd include it because this is stuff I'd never even heard about. It's called a preon star. Um, it's much weirder than the ones I already described. So probably it's a lot less likely, but I wanted to mention it anyway. So it's a proposed type of exotic star made of preons. What are preons? I didn't even know this. Basically, they're these hypothetical subatomic particles that are even think of it like an atom. I think an atom is Latin for like indivisible, right? But then people discovered, oh, it's made of protons, neutrons, and electrons, and then even further, people discovered that those were made out of quarks. So the preon's like the next level down. It's like quarks and electrons and things like that would be made out of preons. These even smaller subatomic particles, or I guess like subatomic particles. Um, so they could be the subcomponents of quarks and leptons, similar to how um, protons and electrons are made of quarks. And I'd never heard of these before. It's a theoretical model. There's no experimental evidence to support this. But again, there's none to, I guess, directly disprove it either. But preon models were pretty popular in the 80s, but they lost interest since because this turns out what our current model of particle physics, the standard model, it does a pretty good job. It does a mostly correct job of describing physics. So there hasn't really been a need for a preon model. And there's been no direct evidence to support it, so it kind of lost favor. However, theoretically, you can get stars that form due to these preons, just like how you can get quark stars from neutron stars. You can get preon stars maybe out of quark stars or something like that. I'm not sure. So they'd be even smaller and denser than quark stars or these electroweak stars. I'm not sure too much about them. Apparently, they might be able to originate from supernova explosions or even during the Big Bang. Um, and additionally, they're a potential candidate for dark matter because I guess they'd be very, very hard to see. But again, we have no proof of this. It's just one of these. It's probably a paper someone wrote somewhere, did some math, and they said prions might be a thing, and I guess you might be able to get stars out of them if they exist. So that's a pretty wild one. I just wanted to include it because it kind of gives you some scope about different what physicists do. They propose a lot of things, and sometimes they're right and sometimes they're not. Maybe prions are real. Who knows?
Well, I wonder because I heard the term dark star before, and I don't know if it's related to that at all, but because you could imagine some kinds of stars, like what are really stars, right? Like star that you can't see or can't observe in the visible light, which is if it's have some kind of nuclear reaction that I don't think you can have that. That so there might be some kind of dark star that exists in some kind like in the period of the early universe, but I don't know how credible the theory on dark star is. I know there must be some sci-fi movies. I know I heard from like I think some metal music talk about dark star, but not in the at least in my experience of the scientific domain.
Yeah, I think dark stars are technically under this categorization of these hypothetical stars that I wanted to talk about today, but I'm not going to. So I do plan to talk about those in the future. I think black holes actually might have been called dark stars when they were first proposed as well, because they're like they're a collapsed star, and then they form some new object that looks like a star. Like I know back in the early days of black holes, people called them stars as well, and then they kind of differentiated them. They said, "Oh, they're a bit weirder than stars, so let's call them their own thing."
Right. In a way, it's like almost like by definition like a dark star almost, right? Because instead of emitting light, it absorbs light. So it's basically dark star. Oh, problem solved. Dark stars are black holes. Black holes are dark stars. Perfect.
And
Easy.
then this final type of exotic star I'm going to propose, you could it would be invisible. So it's kind of like a black hole in the sense that you can't see it. Basically anything you can't see with like light is a candidate for dark matter because you can't see it. And that's what dark matter is. It's this matter that we're predicting is out there, but we can't see it with it interacts gravitationally, but not optically, I guess, not through the electromagnetic spectrum. So this final type of star, which this one I've actually heard about before, it's called a boson star. Um, so it's another one of these hypothetical exotic stars that consists of bosonic particles, whereas most of the stars, like all the ones we've talked about already, consist of fermions, which are subject to this Pauli exclusion principle.
I thought you're
Bosons,
gonna say BEC stars.
I think that might be another name for them, but anyway, these bosonic stars, the bosons in them can all clump together in the same quantum state, just like a Bose-Einstein condensate, which I talk about a lot in the first episode as well. So these BEC gases, they're these macroscopic quantum objects that occur due to the bosonic properties. So because these bosons can actually occupy the same quantum state, unlike fermions, they kind of get this quantum pressure that acts as if there's force. They get this thing called a quantum pressure. It's different than the quantum pressure that fermions have, but it's there nonetheless. And bosonic star would kind of have a similar thing going on. This condensation of states would allow this quantum pressure would keep the star from collapsing in on itself. In my mind, when I first read about boson stars, I was like, okay, like helium's a boson, or some types of helium is bosons, and there's helium in stars, so maybe it's made out of that. But the only one people seem to care about is if a boson star that's consisted of particles called axions. So, what is an axion? I don't really know. The internet told me that it's this kind of hypothetical, it's an elementary particle that was originally postulated to resolve the strong charge parity problem in quantum chromodynamics. So there was a mathematical symmetry problem in quantum chromodynamics, which is this theory of quarks and things like that. and somehow an axion was a proposed kind of hypothetical particle to deal with this.
So the one star, the one boson they care about that form stars, the one that are hypothetical rather than the one that known to exist.
Well, they probably, I'm gonna guess that if you tried to make a boson star out of like helium or something, you get a lot of problems and things that cause it to not form. Um, but somehow with these axions, maybe you could.
So axions are something that people in my old group used to research, and the detector that I was working on was used in some cases to search for what's known as a solar Kaluza-Klein axion, which is an axion produced in the sun that we could then detect with these dark matter detectors. Um, but yeah, it's just a lot lighter version of dark matter compared to, say, a WIMP or a weakly interacting massive particle. And yeah, it's another dark matter particle out of the few that are valid in their suggestion.
Yes, if I learned one thing today, it's that there's many different types of particles that are kind of theoretically proposed and to solve problems, but we don't know if they're real or not. And a lot of these exotic stars are, I mean, we know quarks exist, right? But imagine a lot of these exotic stars are like, what if this exotic form of matter we don't know exists made a star?
It's like a permutation problem. There's like this many quarks or elementary particles. You combine in specific ways, and you name them, and you're like, can we find them? Well, can stars form from them? Well, can you do this with them? And there are many combinations of those.
Yeah, I think the logic with the stars maybe was that if these, it's one way to confirm, it's one way to confirm if these hypothetical particles existed or not. Because if you find a star made out of them, well, there they are, right? Maybe that was part of the goal with studying stars made out of these particles. Um, but anyway, axions are maybe a thing. They do pop up a lot. I know that in particle physics and this standard model stuff, people talk about axions a lot. So people do care about them a lot more than preons, I'd say. But unlike normal stars that emit radiation due to gravitational effects and nuclear fusion, boson stars would be completely transparent and invisible because they're made of these axions, these particles that are a candidate for dark matter. Um, so these bosonic stars are actually candidates for dark matter as well. The immense gravity of a boson star, it could bend light around it, creating an empty region kind of resembling a black hole. And like a black hole, it would absorb ordinary matter as well, actually. But because of its transparency, matter that would probably, the matter which goes around it or orbits it or gets pulled into it, it would heat up and emit radiation like you see around a black hole. So that's one way you can maybe detect them. And actually, this matter would be visible at its center as well. So that's kind of weird. It's like a black hole, but you can now see into it. So that's something I think a lot of people are interested in. And the reason why I know about these boson stars is because our previous guest, Andrew, his supervisor, Sergey, has actually written some papers on these recently, on boson stars. They're kind of starting to pop in the literature a little bit. I'm not sure. I didn't read them. I don't know what he talked about them or how he studied them, but I do know some people are interested in them. And one weird thing about them is because of these bosonic stars being transparent, you could see what's in them. Somehow, if you rotate this, they've done simulations, a rotating bosonic star, um, it would form a torus or a donut shape, as the centrifugal forces would give this bosonic matter this kind of donut form. So there are these pretty wild theories out there that hold on, I have it written somewhere here. Yeah, it's been hypothesized that these dark matter halos that surround most galaxies, so dark matter halos are a huge thing in astrophysics. They're talked about all the time. They surround galaxies and they kind of account for some extra mass that we can't see. Maybe these dark matter halos are these big toruses, these big bosonic stars. So there's theories out there that propose that, although I don't know how much I believe that. That seems pretty wild to me. And additionally, they might have, yeah, they're potential candidates for kind of early Big Bang physics as well. a supermassive boson star could exist at the core of a galaxy, for example, that could have came from the Big Bang or something like that. And it may explain kind of these properties of these active galactic cores that we aren't able to describe currently. Pretty much me just repeating I don't really know a lot this episode, but it's really cool stuff. It's very like sci-fi, and I'm kind of into it. Um, I think quark stars are probably the most realistic, but bosonic stars they're picking up. Um, there's currently no significant evidence that these stars exist. But there are candidates for them out there actually. You could detect them just like you detect gravitational waves from a black hole. If you have two black holes orbiting one another, um, these bosonic stars, you might be able to detect the gravitational radiation from that. But if you're very far away, I don't know how you distinguish that from two black holes rotating as well. So it might get a bit tricky.
Well, like what we discussed earlier, a lot of people don't know what these are, even the people who study them. So it's okay to say, I don't know. But who knows, maybe you'll be able to do some theory relating to boson stars with your black holes and your catastrophe theory and whatnot.
Yeah, I wouldn't count on it. Yeah, there's most of physics is just we don't know. I've decided after studying it for not even that long, only like 8 or so years.
Well, thank you very much, Liam, for the very interesting topic. And for those of you that do know at least something about something in science, whether it's a very interesting specific topic or it's your area of research, we would love to have you on the show. If you are interested in being a guest, there are many different ways in which you can contact us. The first being our Google account. So you can send us an email. We are hyperthesispodcast@gmail.com. So you can send us an email if you have questions, if you'd like to be a guest on the show and you're an expert in the area, or even if you're just a student in the area in which you focus. And it doesn't just have to be physics. It could be whatever science-related topic or math-related topic that you'd like. You can also contact us and find us on Instagram. We're at the Hyperthesis, where we post updates about episodes. Our last episode was just a little bit late coming out, and if you were following us on Instagram, you would have seen that, and any panic would have been distilled from you. We are also on YouTube. You can check out our videos there. They are masterfully compiled by Feely and his MacBook, and they do look really cool, so you get something pretty to look at while you listen to the episodes. We are on pretty much any podcasting service out there. We're on Amazon Music, which I think is now Audible. We are on Google Podcast, Apple Podcast. We are based out of Spotify. We used to be based out of Anchor FM, but now it is Spotify. And yeah, find us, rate us, give us a like, subscribe, whatever you do on the whatever podcasting service or however you find us. And if you have any questions, comments, concerns, or you want to be a guest on our show, send us an email or a direct message. So, to finish off today, we did talk quite a bit about bosons, and it's very interesting where the name boson comes from. It was originally proposed by Dirac to be named after a very well-known physicist named Satyendra Nath Bose. And this was to honor him. He was still alive at the time, but this was a way to honor him and his research that he was able to do. Now, Bose was born on January 1st, 1894, in Calcutta, which is now known as Kolkata. I think I'm pronouncing that right. And he was the eldest son of 7 children in his family. He was actually the only son. He had 6 sisters, and being the oldest, he was able to advance quite quickly through school, as we've seen with a lot of these famous mathematicians and physicists. Now, his schooling began at the age of 5, and in his final year of school, he was admitted to the Hindu school in India. And he was able to pass the entrance examination in 1909, and he stood 5th in the order of merit. So out of everyone that took the examination and applied, he was number 5, which is really good. Once finishing the Hindu school, he was able to start his journeys into science. Unfortunately, not much else is known about his early life, but he was able to go to the Presidency College of Calcutta, where his teachers included another Bose, this time Jagadish Chandra Bose, and a couple other Indian physicists and mathematicians. Now, Bose received a Bachelor of Science in what was known as mixed mathematics from this college, Presidency College, in 1913. Now, at this age, he was just shy of 20 years old. Once he finished, he joined Sir Ashutosh's Mukherjee's newly formed science college. Apologies for butchering that name, where he then completed a Master of Science in Mixed Mathematics in 1915. And his marks for his MSc actually created new records, which have yet to be surpassed. So truly, he was quite the genius, quite the prodigy. He wasn't as young as some people we've talked about, but he was still very, very excellent at what he did. And after completing his Master of Science, Bose joined the Science College at Calcutta University as a research scholar in 1916. And that is where he started his studies in the theory of relativity. Now, relativity was still a very new topic, Einstein having just introduced it not too much earlier. And this was a very exciting time to get involved in physics, whether it was quantum theory or relativity. And during this time, lots of stuff going on in physics. There was also a lot going on in his life, including getting married at the age of 20. Now, I know the three of us, none of us are married, and we are well over 20. So being able to handle a family along with physics, that's quite the achievement. Now, Bose went on to begin studying these new and advanced topics, and he was also a lecturer in the physics department at the Raja Bazar Science College in the University of Calcutta. And he was also able to write in English, which was an excellent asset to have, so that he could communicate all of his ideas to the English-speaking world, which, as we know, science is mainly done in English. Now, starting in 1921, he joined as a reader, which was a very specific position, which is more so in Commonwealth nations from the UK and India was, and I think still is, a Commonwealth nation. But it's essentially a senior academic. So he was joined as a reader in the Department of Physics at the University of Dhaka, which is in present-day Bangladesh. And there he was able to set up laboratories, he was able to teach advanced courses, and he was able to do a lot of very good research. Some of this research included deriving Planck's quantum radiation law without any reference to quantum physics. And this was a very novel way to do it through the use of counting states with identical particles, and really expanded on the ideas that were first introduced by Planck. He actually didn't get accepted for publication, but he sent it directly to Einstein himself, and Einstein was able to translate it into German and submitted it to a German publication, which at that time was a very, very big publication. Because of Bose's work and people realizing that, hey, he's really knows what he's doing, he was able to work for 2 years in a European X-ray and crystallography laboratories, where he worked with de Broglie and Curie and Einstein. So that is like a power foursome there, those four working together. And while working with Einstein, he and Einstein came up with what are known as Bose-Einstein statistics. So through this work, they were able to essentially look at some quantum mechanics and statistical mechanics, which we won't get into now. And because of this work, Einstein was able to translate Bose's work back into German again. And the title of this work was Planck's Law and a Hypothesis of Light Quanta, which was published in 1924. Now, from this, and as a fallout from their work, Liam, you will know what comes next quite well, but they were able to come up with the idea that eventually led to the discovery of the Bose-Einstein condensate. And so Bose and Einstein were able to work on this, which again, this work was rejected quite a bit. A lot of Bose's work was rejected, but he was able to work with Einstein. And this Bose-Einstein condensate, which is a dense collection of bosons that are supercooled, and we've talked a lot about them before, was demonstrated to exist even after Bose's death. In 1995 is when the first Bose-Einstein condensate was produced. But they predicted it many, many decades earlier. Now, after a stay in Europe, Bose returned to Dhaka in 1926. He didn't have a doctorate at the time, and so he wasn't technically qualified to be a professor, but through the recommendation of Einstein, he was able to be a professor and went on to make great achievements there, including heading the Department of Physics, and also becoming the Dean of Science at the university. He was also able to design his own equipment for himself for X-ray crystallography, and he had his own laboratory. So he did a lot of work with gases and X-ray crystallography. Now, when things started to be shaken up in India more, he returned to Calcutta, and there he taught until 1956. And there he, again, did a really fantastic job, especially in encouraging students to do their own research and design their own equipment, and something that would be cool today even. Now, he also focused on other fields aside from physics, including biotechnology and literature. He also made studies into chemistry, geology, zoology, anthropology, engineering, and a lot of other scientists. He was truly a very well-balanced person, and he was very pivotal in making sure that education was available for people within the regions in which he lived. Now, he was also nominated for the Nobel Prize several times, and I don't believe he ever actually won it. Correct me if I'm wrong. But Bose leaves quite the legacy. I mean, there's still research, both theoretical and experimental, and simulation, that's based off of his work. And unfortunately, we did lose Bose several decades ago on February 4th, 1974, at the age of 90, where he died in Calcutta, close to where he was born. So truly an incredible person, and we have so many things in physics named after him because of his impact. And I think that's quite outstanding. And the fact that he saw so much failure, especially with trying to submit these astounding publications, it just says something about who he was and how he persevered.
All right, thank you, Patrick, for the story. And that's gonna be the end of our episode for today. So I'll see you guys next time. Take care.
See ya.
Bye, everyone.